geometry of the perceptron. Okay, and it's a good idea to do problem 1.2 in the book. Okay, if you're completely unfamiliar with the geometry of the perceptron. I'm going to discuss the geometry in 2 dimensions because it's hard to draw in more than 2 dimensions. Okay, so let's simplify to the case where the applicant is represented by 2 numbers, not D. Okay. And let's imagine that we collect for an applicant age and the income. Okay. And we're looking at this function sine of W transpose X. So this is the weight vector, this is the input vector. The input vector X, so X is equal to 1, remember it's augmented with 1, age and income. Okay, and corresponding to this W is a W0, W1, W2. Okay, now the nature of this linear function W transpose X is that it defines a line. So if we ask what is the solution to the equation W transpose X equals 0, okay, that's going to be a line. Okay, so this is W transpose X equals 0. Now, in D dimensions, this is called a hyperplane. And when you define a hyperplane, there are 2 things that are relevant in a hyperplane. The first is the sort of the slope or the orientation, and the second is the position. So I can have the same slope and move it up and down, and I get a different position. So the position is related to W0, and the orientation, the slope, is related to W1 and W2. Okay? And typically, so this W1 and W2 define the normal. Okay? And okay, so that's the solution to W transpose X equals 0. And then on one side is going to be positive, and on the other side is going to be negative. So there's a positive side, which I will call the +1 side. Okay, and there's going to be a negative side, which is the -1 side. So this is the equal 0, then this is less than 0, greater than 0. Greater than 0 results in +1 when you take the sign. Less than 0 results in -1 when you take the sign. Okay? So that is the geometry of a perceptron. Okay. Now, I want to sort of consider the criterion on the basis of which we're going to decide which one to pick. Okay. So let's consider a second perceptron. So if I have another one here, okay, age, income, okay, and this might be sine of W prime dotted into X. So I'll use dotted into because it's inconvenient to write the transpose for W prime. So this is W dotted into X. That's the same as W transpose X. This is W prime dotted into X. That's the same as W prime transpose X. Okay, now because it's a different set of weights, it could have a different orientation and a different position. So let's say this hyperplane is over here. Okay. And for this hyperplane, you've got a different normal, okay, and a different +1 region, and a different -1 region. So this is +1, this is -1. Okay. So, when Malik was sitting down, he had to decide, by choosing an appropriate set of weights. For example, imagine that Malik had to make a choice between these sets of weights W and these sets of weights W prime, i.e. between this classifier of people and this classifier of people, and he chose weights. Okay, so he had to decide, he had to pick one of these. Imagine his choice was only one of these 2. Okay, now we've gotten rid of Malik, okay, and we're going to ask an algorithm to decide. Okay, and so let's ask the question, which of these is better? And immediately you should think to yourself, well, how do I know which one is better? Okay, and we don't until we realize that, we do have data. Okay. So let me show you what data looks like. Okay, so data is a bunch of applicants. Okay, so you have a bunch of applicants, and what are applicants? Well, an applicant comes with an age and an income. So an applicant is a point in this space. So imagine I have a bunch of applicants. Okay. Now, on this picture, those are the applicants. On this picture, it's exactly the same set of applicants. I have a bunch of applicants. Okay. And, we have a bunch of applicants. Okay, so that's what the data has. It contains a bunch of applicants, age and income. Okay, but the data has more. The data tells you for each applicant whether or not they paid off their credit. In other words, whether the correct value of y is +1 or -1. So now what I'm going to do is I'm going to use blue circles to represent +1, blue corresponding to the +1 blue here, and red X's to represent -1. So imagine that these guys all paid off their credit. Okay, so they're +1s. And imagine that these guys both defaulted on their credit, so they are -1s, represented by a red X. Okay, so this is not a good red X. Let's see if I can get a better red X. Okay, red X. Okay. How does it look like? It's the same applicants. So these guys are red X's. Okay. And correspondingly, we've got the blue circles. Okay. Now, I'm going to ask you again. Which of these hypotheses is better? Pause the video. Okay. 1, 2, 3. Okay. I'm back. So if you pause the video and thought, this is the better, well done. Okay, you're implementing a very natural approach to picking the quote-unquote better hypothesis. What you're saying is that, look, this hypothesis said blue for all these points and red for these 2 points. So it disagrees with this guy and this guy. Okay, whereas this guy said red for these 2 points and blue for those points, so it agrees with all the data. So this guy looks good. Okay. This guy looks bad. In particular, there are 2 data points on which it looks bad. Now, we mentioned before that looks can be deceiving. So just because it looks good, it looks good on the data. Okay, and it looks bad on the data. Now, just because this looks good on the data, does that mean that G equals F or G approximately equals F? Well, that's an issue we will talk about in depth later. But for the moment, okay, we have a criterion on the basis of which to pick. Okay, so criterion to pick. Pick the hypothesis that looks better. Okay, so in other words, when we talk about looks, we mean how does it, compare with the data? How does it look with respect to the data that you have? And when you have data, it's natural to pick this guy because it agrees with the data. This guy doesn't agree with the data. So that's the criterion. Okay. And now we have to implement the criterion and actually do the picking. And you say, oh, well, so now so remembering that, the geometry of the perceptron is that it produces a hyperplane or a line in 2 dimensions. One side is blue, one side is red. How do we pick the one that looks the best? Oh, just look at the data and pick it. Okay. Well, that's a perfectly valid algorithm if you can look at the data and if it's obvious how to pick it. Okay. But in general, your data set is not going to live in 2 dimensions. It might live in, 1,000,000 dimensions or even 100 dimensions. And we can't visualize and we can't look at the data and pick it. So we need an algorithm that implements this criterion and picks the hypothesis that looks the best. Okay? So pick the hypothesis that looks better. How? Okay. So those are the 2 goals that remain. Okay. So we have a hypothesis set. We have identified a criterion by which we're going to pick, and now we need to identify how to do it. We need to give you a way of doing it. Okay. So let's address the how.